Hello everyone, let's solve true coprime today. It's a very typical DFS problem. So let's try to take a look at some examples. For this example, for each node, it asks us to find the closest ancestor, like whose value is coprime with current node. So for example, for this node, the node number is 2, the value is 3. It has 2 ancestors. For this ancestor, its value also 3, so they're not coprime. So we cannot return 1 for this node. Let's take a look at another ancestor. The value is 2, and the node value is 3. So these two nodes are coprime. So for node 2, the closest ancestor, like whose value is coprime, are node 0. Okay, so how to solve this problem? The naive implementations for each node, we can keep finding its parent. We can keep finding its parent. Then for each parent, we can check if the value are coprime. If it is, then we find the node. Then we know in what cases the tree can degrade it to a list. So it may take O(n) to find a value for each node. So in the worst cases, the algorithm can be O(n) square. So it might be TLE. Then we need to find a better solution. Let's take a look at the constraint. That's a very important constraint. So for nums I, there are only 50 possible values. So keep in mind, it will be very useful later. Okay, so let's take a look how to utilize that constraint. If for each node, we can maintain an ancestor list. In this ancestor list, we know there are at most 50 different values. So for each value, we can maintain a most recent ancestor. If we have this ancestor list, then for each node, we can just try at most 50 ancestors. So we can find an answer for each node within all 50. Okay, let's see how to do it. So first, the DFS call starts with the root node. Then the ancestors is empty. So it's -1 for the root node. Okay, then root node call its first children. Then we update ancestors. The ancestor is in this format, value node depth. So for this node, when it calls the first children, we know the ancestor is, and the value is 5. The node number is 0, and the depth is 0. Okay, so for this node, its value is 6. 6 and 5 is coprime. So we'll find answer, which is node 0. Okay, then this node calls its first child. And it's updating the ancestors. No, value is 6. And the node number is 1. The depth is also 1. Then for this node, the value is 2. 2 and 6 are not coprime. But 2 and 5 are coprime. So we return 0. Node number 0 is answer for this node. Okay. And for this node, its value is 3. 3 and 6 are not coprime, but 3 and 5 are coprime. So node number 0 is also the answer for this node. Okay, now we're calling the second child of the root node. 10 and 5 are not coprime, so it's -1. Then this node calls its first child. It pushes the node to the ancestor's value is 10. Node number is 2. Depth is 1. 6 and 10 are not coprime, but 6 and 5 are coprime. So node number 0 is also the answer. Okay, for this node, we know 15 is not coprime with 5 or 10, so -1. Okay, now we can get the answer. The answer is -1, 10, 0, -1, 0, 0, 0, -1. Okay, let's see how to implement it. First, we use adjacency list to represent graph. So we preprocess the edges to build my graph. Then we need to maintain these ancestors, and we have a result array. Finally, we will return this result array. Okay, and we have a Dfs function. In Dfs function, we start with node 0, and the steps is 0. The parent is -1. Okay, and for this ancestors, note I pass by reference here. So we need to pay attention that we need to update the ancestors and eliminate the side effect in some branches. Okay, so first of all, we need to update my closest ancestor for current node. We just need to iterate all the ancestors and find the closest ancestors that satisfy my condition, which means the GCD of the values are 1. And as long as the depth is smaller, then we update my closest ancestor, then just assign my closest ancestor to my result. Okay, next, what we need to do is we update the ancestors list to insert my current node. Okay, next, I just iterate all my neighbors. Note, we need to skip the parent node. That's why I pass parent here. Then for each child, I just recursive call it and make depth +1. The code cannot pass cases since we pass by reference here, but we always insert insert new value or update value of my ancestors, assuming that I have 2 children, and here I first call the first children. In first children, it update my ancestors. Then I call my second children. So the effect of the first children is still there. Since I pass by reference, if it's not passed by reference, if I remove this reference and pass by copy only, then this code works. But I want to improve some space complexity. Like I don't want to copy my ancestors for each recursive call. So I pass by reference. So each side effect, we need to revert it. So I keep an original node here, and I keep a Boolean variable called has original node. Then after the recursive call, I will check, I will try to erase the side effect. So my the second branch will not affect the third branch. The fourth branch does not affect my second, third branches. Okay. So we know that nums I is greater or equal than 1 and small or equal than 50. So time complexity is all 50. And since I will visit every node once, for every node I will check all its ancestors. And we know that at most 50 ancestors for each node. And for space complexity, it's also ON. Nums is input. The graph is ON. This is adjacency list, and we have at most ON edges. And for this result array, it's ON. For this map, it's just O50. Since there are at most 50 elements in this ancestors list. And we know we also have this recursive call. Recursive call is using the memory in stack. And in worst cases, the tree degraded to list, we know there will be at most ON recursive call. So it also takes ON space. So in general, the space complexity is also ON. Okay, that's a problem. Thanks.